Thank you very much, Manu. Yeah, so um, that was actually a very interesting topic because that's something that is very new and that is based on discussions that we had uh, with um, with Guillaume and Manu. It's about how to use actually Simba Online for presenting models and being able to share them, like for tutoring, lecturing, even presenting paper posters during conference. Wait, let me share my screen. I suppose that you will be seeing it.
Yes, it's working now.
Okay, great. Um, so yes, I'm from the Institute of Energies of the University of Applied Sciences in Western Switzerland. So it's really about applied research and development. We are sort of linked between academy and industry. So we are really bringing new developments to to make them industry ready. One of our tasks is also teaching electrical engineering on bachelor and master level. And also we are offering some engineering and consultancy services to the industry, but I'm personally mostly interested in teaching and applied research. And for this, we are using several tools. One of them is SIMBA. Myself, Daniel Siemaszko, I did work at CERN. I did work in the industry with Hitachi Energy and ABB. I also worked in the academic world. And from July, I just took this position as associate professor. And just before I took the position, we had long discussions with Manu and Guillaume. The question was about, yes, how to share models, SIMBA models during typically lectures, tutorials, and maybe also the situation of a conference where we are presenting a poster, for example, and you would like to show some curves and moving things with your tablet, that tablet that would have maybe only a connection to the internet with a web browser, not necessarily the full program running. It is quite useful, yes, to deliver those live simulations in a web browser, also to share interactive circuit links that the audience could check. Imagine a tutorial, like I've been tutoring about some specific uh, average models for DC grids, DC microgrids, and then the way the models were shared was with the full model, and then we had to arrange licenses, which was a bit cumbersome. So yes, typically we're addressing this typical application, lectures, tutorials, and conferences. So we're discussing with Guillaume and Manu just before I took my position. So I was like, hey, listen, like, it would be really nice. For me, the ideal environment would be, first of all, like you share something that the audience wouldn't need a license for, with a shareable link that we can just give as a QR code or just like a clickable link that you can also, for example, share on your LinkedIn page. Hi, I just sharing this new model. Check it out. You don't even need to have Simba running. You just can open it on the browser. So web-based, no local application. That is really useful for typically like students that are not necessarily in power electronics, but so they don't necessarily have the tools, and you just still want to illustrate some topics on them. While discussing, I was telling them, because Manu asked me, hey, tell me, what is your ideal tool? I said, well, it would be nice to have the possibility to upload my own specific models, because every single engineer or professor has their own ways of building the models or teaching it. And also, it would be nice that the user could modify those models and parameters, and also possibility to update models to keep with keeping the same links. So you have maybe a sort of like model with a portfolio that is growing, and you don't need to regenerate a link. So that was the idea. That was the wish, and well, Manu came with a SIMBA Cloud does it all. So that's really fantastic. I'm really happy, and I started using this year with the students. We can go like first for a very simple example. That was the very first example that I used, using with a simple PLL for AC grid voltage. There is a QR code, so yes, you can check it with your mobile phone. The interface is not ideal for mobile phone. Maybe so there's some responsiveness to add to it, but I'm not sure if it is the goal to have it with a phone. But if you click, if you copy, what shall I do? Shall I copy paste the link? Wait a minute.
You want to put the link in the chat?
Yes, that's what I will do.
I can try to do it.
Wait a minute.
Yes, Daniel, you can copy and paste it in the chat.
Actually, the link, when I open it, it says that it has expired, that the sharing link has expired or is no longer available.
How can it be possible? Because
Have you set it as public?
yes, but how can you click on that link?
Oh, yeah, I do have, I do have it.
Okay, so I copied, and I will open the chat, and here I will
Yeah,
copy
but
paste it in the chat. It should be
it
fine.
doesn't seem
Anyway,
to work, huh?
I put it in the chat. So I took it here. This is the model I want to test, and I can download it. You can open it online, and I can share it as a link. Also, I can replace it or change the access right. I can suddenly put it like not accessible. But if I open it online, do you see SIMBA online now?
Yes.
Yes. This is a very simple model. As you can see, we are having like just grid voltages with a selector, because I added some deeps in the grid network. I don't like ideal grids. I like grids with faults and disturbances. Then if I come, this is a model from SIMBA directly, just a Park transform, and it's a very simple way of implementing a PLL. It will just keep the Q component to 0. Inside we can look at it. There's a PI, it's a PID, but the D component is 0. Those are parameters, KP and KI, and a small transfer function that is actually simply a filter. We have here then our integrator, and that will limit the triangle to 2 pi and 0. Okay, and we output theta. Theta is used for the transformation. Let's run it. Okay, it ran already. You know how fast it is. And we can, for example, check. We have the networks. We see the network that we are testing it. Here at some point we have a deep, and we will see um, how the PLL will respond to that. Let's check at the angle. We see that first of all here we have a little adjustment moment, because of course the integrator starts at a very random position that does not correspond to the grid. So after 2 or 3 periods, it is synchronized, and we have here the deep, and we will see how it impacts the D and Q component. Here we see that we have a very quite a big second harmonic, which is due to the asymmetric state of the grid. At some point, that was hardly noticeable here, but we have another phase jump on the grid, which is maybe not so realistic that way, but it has the advantage of testing the dynamics of the PLL. So this is all possible to use. Maybe you can run it in your own browser. Oh, Guillaume says it's working. Thank you so much. So the goal was to have something very simple, easy, that you can then play with. You can change parameters and rerun. Like, does it work for a 60 Hertz grid? Let's find out. Yes, it does. Well, surprise. So this is something that that is now that I am using sometimes, like with this kind of not a QR code, because we are not using it for with the phones, but the students can just click on the shareable link that is like printed in their PDF handout and material, and they can like play with it to understand better. Well, in the title of my presentation, we're talking about DC-DC converters, not about PLL for AC grids. You might, maybe some people that we met already online, like last year for the SIMBA conference in 2024, where I presented some system level modeling of DAB for system level modeling of DC microgrids. And you can see, so this model was simplifying the function of DAB with current and voltage sources. And we were, the model was implementing the integrators for the capacitors that were on each side of the DAB, and the current flowing through the MFT was also modeled with the ideal values of the series inductor, and we were also having the idea of winding ratio. And this model was having current controller and a voltage controller. The idea was to compare between switching and average model, especially from the terminals of the DAB. We are interested in what's happening on the DC side, not inside, because like if we check this like full model of a DAB that I modeled like some time ago already, that you can get like on this link from my GitHub. We are maybe not so interested in the switching state, but we are interested in the fact that if we use an average model, that we have the same behavior on this DC side. So in terms of voltages, but also in terms of RMS current. Basically, my tutorial last year and in some other conferences was about using this kind of models for going like a bit deeper in the modeling of DC grid with system level models, system with average models. Sorry. So I uploaded a bit more complex model. Maybe I can also do the same and put here in the chat the new link that you may open, and then yep. So here in this model, we have a full DAB with here an MFT. There are three different models in here. Here we have a simple current control with ideal voltage sources. Here we have voltage controller with the capacitor on the secondary side and voltage, the current source as a load. And we have also the system level SST block, the very one that I presented you. If I go inside, open, so I have a voltage controller setting, giving a current set point to my SST cell. That one, by the way, can then be parallelized. We can put input and output in parallel or series to reach MVDC stage. And here we have the model, so you can check, go a bit more in details. You have the current controller, that is a very simple current controller without limitation. The MFT model, we have the capacitor models, and if we go one step higher, the voltage controller, that one is implemented with P part, integral part, and homemade anti-windup. I suppose that there must be some things like this in the libraries now, but I just kept it because I like it that way. And if we run the model, let's see what happens. So we have here the indicator that it runs. I think this model is a bit more complex than the PLL model that I showed before. It has a bit more parameters. But yes, it finished. Let's see. We might be interested in. This is the output volt. No, this is not this is the grid voltage, not the one I'm interested in. This is the current, the load. Yes, that's a bit more interesting like this. We see in red, it's the DC current load, so very idle current, and what we see in blue, it's the input current. And this is the current on the MFT side, but secondary side, the one that is answering to the DC current load. Maybe we can add a scope and check our voltages, especially on the secondary side. And we have here a behavior of the output voltage that is quite fair when compared to a simulation of a switched model, and also like in some papers that I am referring to in the previous tutorial, it is also very similar to real experimental setup. Okay, maybe we would like to see how to compare it to the detailed model. Let me run it. That one will go a bit slower. I still have some 4 minutes. You can see it's running here. That one, just while waiting, has it's a very detailed model. If we go to inside the modulator, yes, so we have a self-made modulator because that one is using on phase shift modulation. It has a specific carrier and a reference handler, and it generated the pulses while including also the dead time, the phase, the duty, and the period. The duty is fixed, the period is fixed, only the phase is changing. We have also a so-called sampler. If we go here, the sampling is simply taking care of the fact that references come in only at the beginning of a period. It's a way of ensuring that DC, the simulation is completed successfully. It's a way of ensuring that there's no DC component, unwanted or uncontrolled DC component. That's the sampler. And here we have the controller that I had to rewrite because one drawback, maybe Manu can talk about it, of SIMBA Online is that it doesn't take C blocks. So you have to really do everything in this block, the kind of blocks. Okay, Let's check if we can see some of currents. Very good. CP2 current. So we have here current that are happening here and here. Maybe we can add a scope and would be interested in the voltages, V1 and V2, I believe. Yes. Let's see if we can zoom in it. Oops, sorry. Yes. Oh, what happened? It's a, oh yes. Oh, okay. We can zoom maybe in it. So we have a typical TIB behavior. Just one aspect here that is a bit strange. You have a very strong DC component in the current. That's something that I'm still working on. But on the voltage side, we have this this behavior that is very interesting here. And otherwise, yeah, that's it. We can also compare the behavior here of the current that is very similar to the RMS one, to the average one. And also on the voltage side here, we can see if we look into C1 voltage, yes, the green one here. Yes, we can really reflect, we can really recognize the value that we had before. Okay, well, I think that's it. That's all I wanted to show.